Is my screen visible?
Yes, sir.
Good. Thanks. So last time we have been seeing problems from week 3 and week 4 so far. So would you like me to continue that?
Yes, ma'am.
Yeah. Then if you have
Ma'am,
any doubts in the practice assignment or anything, you can ask me now.
ma'am, can you please dress up the concept of steady state error?
Steady state error you want to revisit. Okay, fine. We can. Okay. So, in our control system, we used to have two types of control system. One is open loop, where you give some input and expect some output. Another one is, let me call it as open loop. The gain will always be, the forward path gain will always be G in both the cases. Okay. So, in the closed loop system, you will give one output, but sometimes that, for example, if I give my fan to 220 volt and expect it to run at 220 rpm, let's say. So if this physical relation between this input and output is stable, or for example, if the physical build is very stable, or if you know the physical relation of any system, for example, if you know what the resistance of the fan, what is the capacitance of the fan, if it is ideal, then this will give, whenever you are giving 220 volt, this will give 220 rpm. But in ideal case or in real time, you would not expect this. Even if you give 220 stable voltage or stable input, you might get 200 rpm or 230 rpm. It's not possible to maintain at 220 rpm because of this non-ideal scenarios. So in that case, you will consider taking the feedback from the output and giving back it back to the input. In this manner, you will know what is the difference between the actual output and the expected output, so that you can make some corrections to take this actual output nearby the expected output. So this is how the closed loop system works. In the closed loop system, I said, right, actual output you are expecting is 220 rpm, but the real output you are getting is 200 rpm. So this difference between these two, that we call it as steady state error. Why this is steady state error, that is not just error, is because the system, real time system, if you give any input, it won't react at the same instance because of the time delays in real time scenarios. So the system takes some time to reach that values. So ideally, most of the systems are underdamped systems, so it would take some time to reach to that final state. So finally, we are not bothered about all the outputs until this point. So finally, what is the output you are getting? That's why we are calling this as steady state. After getting it to the steady state, what is the output? And the error represents the actual versus the expected. So if you get 200 instead of 220, this, after reaching the steady state, still if you get this difference, we call this as steady state error. Okay. So how to find this steady state error for any control systems? So when it comes to steady state error, we always speak in terms of closed loop systems. So for a closed loop system, how will you define a transfer function?
GS upon 1 plus GSR, which is.
Right. Because we consider always negative feedback system, so we will use 1 plus gh, right? So out of this, I am including another one term, that is error here. So far, when dealing with closed loop system, we won't be speaking about the E of s, only we will be dealing with G of s, R of s and Y of s, sometimes H of s when it comes to closed loop system. So since we are considering unity feedback system, H of s will always be 1 here. Okay, right. Now we are introducing another term called E of S, that is the difference between input R of S and the feedback H of S. So the E of S can be written as input, this will be Y of S, sorry, input and the output. The error represents the difference between the input and the output. So E is equal to R minus Y, or Y minus, or whatever you are considering. So this error we are considering this, where this y indirectly represents the feedback h. So y is equal to this y, it's coming back in terms of h, right? So h will be indirectly, h will be here indirectly. So if we replace y, that is the output, with this transfer function, or how do we write this, y by r, right? If we write this, this will become uh, g by 1 plus gh into r, where I'm considering only y in the left hand side. That's where that's what we have written here. Since h is equal to 1, we have left it here, but indirectly there is a feedback here, right? So if you do simplify this, you will have this r by 1 plus g term here. This represents the error. So the error will be r by 1 plus g. When you try to find the steady state error, that is final value, after some point, after it reaches the steady state, what is the output? For that, you will use final value theorem. Final value theorem says is, use numerical value after it reaches steady state. So initially the system will start to work on the transient stuff, and after this transient period, what is the final value? That this final value theorem will give out this value. So when I apply final value theorem for this error E, this term, I will have this. So final value theorem can be written as, when t tends to infinity, how the system behaves in time domain. In S domain, instead of t tends to infinity, is S tends to 0. So limit s tends to 0, the term here will represent that. So your final ESS would be limit s tends to 0, s into your term, error term, r by 1 plus g, h. Okay. So when h is unity, you will just leave that. This is how you will find this is what the actual meaning behind the steady state error. So for steady state error, you can find it directly, but usually we used to give some hints for standard signals, like step, impulse won't be there, ramp, parabolic. These are all some standard signals. Why we leave impulse signal is, we are looking for a infinite time. So impulse input will be there at the particular instant of time. So we don't really bother about impulse input. So we will be calculating this steady state error for all other inputs. Those are very practically available for any system, for any test signals we used to use. We can also use the same for sinusoidal or different kinds of input signal. These are some standard signal you used to encounter often. Right. When you consider a input step signal, step input, how the steady state error would look like. ESS, we are calling it as steady state error, ESS. So you know the formula for steady state error. Instead of R of S, just put 1 by S, the same step signal in terms of Laplace transform. And when you put 1 by S, this S and this S will get cancelled. You will get the term like this. So when you consider this G of S into H of S, will be Kp here. This is for step and unity feedback system. If the feedback is not unity, there will be some term called H, maybe 2 or 3, some numerical number that is not 1 will come, and that we call it as Kp, where this is referred to the position error constant. Why it is position error constant in the sense? So if there are 3 different signals, let's take, these are the 3 different signals we are considering. If you how can I say, you have to do some operation to get the ramp signal from the step signal. What you will do? If you want to get a ramp signal from the step signal, what you will do? see, this is my step signal, right? If I just add 2, 3, for example, this is 1, this is 2, this is 3. So if I keep on adding this step signal at some instance of time, how will I end up having something? At the first instance, this will be 1. There will not be any step signal. At the second instance, that becomes 2, then 4, then 8. It goes like that. So this will become a ramp signal. So when you want to take a step, use a step signal to define a ramp signal, you should integrate it, right? Similarly, when you want to get a parabola out of ramp signal, you should integrate it again. But in the other case, when you have ramp signal but you want to get a step signal, then you will do a differentiation out of it, right? Similarly for this differentiation out of it. So if you connect this to this concept, that is position, velocity, acceleration. So you will have some position data. For example, at this moment I am starting from 0. At another instance, I'm going to end up 2, but I know the time that I traveled at this point. So from this, if you integrate all the positions throughout the value, you will get velocity. Same, if you integrate the velocity, you will get the acceleration. Vice versa, differentiation. So when you give a unit step input, you will get a term where it involves the position error constant. Similarly, when you give unit ramp, you will get a velocity error constant that is mentioned using kV. When you use a parabolic input, you will get a acceleration error constant. Right. This is the relation between this position, velocity, acceleration and step, ramp and parabola input. I hope this is clear. If anyone have any doubt, just ask me. Anything is confusing here? You couldn't grasp that? Should I repeat anything until this point?
No, ma'am.
Right, okay. Okay, we'll move forward. Okay, so these are some visual representation of this, where this is a step input and the system output, where you see the input here. You see the input here and the system output, physical system output. Like when you give step, it necessarily won't give a value like this, right? Because of the real time delays and the physical build of the system, capacitance variation, resistance variation, so many parameters involved in any physical or real world systems. So if you give a mathematically perfect input like ramp like this, you will get some ramp kind of signal out of any system. That is very practically possible. So parabolic signal would look like this. And some features of the steady state error you want to know is, it might be helpful for your exam. Steady state error is a measure of system accuracy, how accurate the system is after some time. If the system behaves as I wish, that kind of measure you can take out of this steady state error value. It's a quantitative analysis, not like this might work, or this is good, or this is better. Not kind of comparative analysis. It's a quantitative measure that you can certainly say about any system. And in any ideal scenario, the system should match the reference input as time progress. Then you can say that system behaves well, or that is a perfectly designed system. And this our idea is to keep the steady state error as low as possible, that you know, so that we will increase the accuracy or make the system to work as we wish. And the steady state error depends on two factors. One factor is the reference input, another factor is the type of the system. So as I usually say is, when you want to solve a problem, you should look for these two input. What input they are giving. Second factors you have to consider is, what is the type of the system. Type means number of poles at the origin. So if it is a type 1 system, for the same input, it might behave in a different way. For type 2 system, it will behave in a different way. For example, I have three system type 0, 1, 2. The same step input will give different kind of output response in all the three systems. So how one input will affect those system also depends on its type. So you should be aware of these two factors, input and type. If you get these two information from any question, you will be able to solve what is a steady state error. And the questions might also be in another way. They will give the steady state error. You will be asked to find any of these things, type of the system, or how, what is the final value. Kind of indirect questions might also come. So you should know all the relation between these factors. See, when it comes to steady state error, you always look for a closed loop stable system. If someone is asking for this, you can understand that the system is closed loop and it is stable, because unstable system exhibit unstable behavior. So you will not expect any steady state or any final value for the system to settle in. So it's always a stable system. Right. Type we already discussed, right? That's just the number of poles in the origin. And many of you have got confused what is the pole and the what is the zero and what is the significance of those things. Just want to brush up those concepts. Poles in general, I will make 2-3 points out of this. So poles in general will be represented using this sign. Sorry, general will be represented using this into multiplication sign, and zeros will always represented using the circle sign. Okay, so whenever we use this signal, zero, it means that it is zero. Whenever we are using this x symbol, it means that we are referring to the poles. Okay, what are the zeros and poles for any system? So for any system, there are two types of representation. One is transfer function representation, another one is state space representation. This state space you haven't studied yet, you will be seeing this in later weeks. First we will be dealing with this transfer function representation, right? So for this, minute. Right. For this, in terms of transfer function representation, you will be having this, right? Output by input will be equal to some numerator term you will have and denominator term you will have. This numerator, whatever is there in the numerator are called zero. Whatever is there in the denominator are called poles, right? So it will be represented in terms of factors, not like a algebraic equation or any polynomials. It will be represented in terms of factors. Even though if it is a polynomial, we will split that into factors and say this many poles are there in that particular system, this many zeros are there in that particular system. For example, if you have some systems like s square plus s plus 1 by again s square plus s plus 1, let's take. Okay, then how will I find? I will say let's take 2s. Okay, it will be easy for me to split, right? So we will split this representation into a factors. Then I will say these are all the zeros of my system, these are all the poles of my system. So I will represent this, this is minus 1, let's take this plus 1. Okay, then I will say two poles. Actually this is 2 times. Okay, and that cannot be distinguished. Two poles are in the minus 1 and two zeros are in the minus 1. That's how I can represent the pole zero representation of any system that looks like this. Any doubt in this? So far?
No, ma'am.
Any other people have any doubt in this?
Ma'am, what is difference between having one pole at a time or having two poles?
Yeah, that you will be seeing in later weeks, because we have to introduce the route harvest criterion before that. Then we can discuss on this. Okay, I need to teach little bit more before that, so that that will be easy for you. I can give you a vague explanation about it, some broader explanation. So when you have a system, for example, this is a system that has two poles in the left half of the split. Okay, so when you get this pole location, I can say this might be s plus 2 and s plus 3. Okay, so I will consider something like this, and there is no zero, so I'm going to consider one above. So these are all the two poles you have. So when you consider, when you find this polynomial for this will become plus 5s plus 6, right? So out of this, if you compare this with the regular system, or any, sorry, standard equation, this will give you omega n is equal to root 6, and 2 zeta, let us consider this as 9. Okay, so it will be easy to split. I'm going to consider 9 here. So this will be root 9. So omega n will be 3. This will be 2 zeta into 3 is equal to 5. Zeta will be 5 by 6, something like this. So this zeta will be lesser than 1, right? Zeta will be lesser than 1. Sorry, it will be 0 lesser than 1, within this range of 0 to 1. So I can say the system exhibits a undamped behavior, right? Some peak overshoot should be there, and at last it is going to reach a steady state value. That I can ensure about this. When you add another pole here, or when you increase the pole location, for example, instead of this 3, I'm going to give 15 or 100. So this is going to drag this term. Ultimately it is going to affect your zeta value and omega n value. So omega n tells at what frequency the system is going to oscillate, or at what frequency the system is going to trigger. Zeta tells you what is the nature of the behavior the system is going to give you. So when you mismatch these two factors, it may affect the output system behavior. In what ways? So adding a pole where you are adding to the left, or furthermore left to the existing system, or nearby the origin of the system, based on this may push or pull the behavior of the system, or make the system go near the instability. So these are all the factors that you consider when adding a pole and zero of the system. So this kind of analysis can be done when you see the concept of root locus or Bode plots, that is going to see in the later weeks. So that will be easy for us to visualize these things in MATLAB or any online platform, so that you will be able to visualize little more than using the words. Okay, right. I hope I answered those questions. If you still have any other doubt, just ask me.
No, ma'am, it's
Right, okay. Okay, I think that's it. If you people have any other doubt, just ask me. If you have any question in the graded assignment, or any doubts in the graded assignment, we can discuss about it. Otherwise, we can meet on Friday.
I have a doubt in
Yeah. Which assignment you have doubt, or general concept?
week 4 first video in the example 1.
Week 4 first lecture. This one. This one.
Yes, ma'am.
Oh,
Yes, ma'am.
okay.
And suppose, like in this question, we are given a transfer function, a reference and output. How
Okay.
do we find that at what time it will get the output? Like here we are saying that it takes 3 seconds to get 100 kilometer per hour speed. How do we calculate it through this transfer function, the
Okay,
time?
this is okay. In this representation, it shows actually this is a MATLAB based representation, so it is very accurate. So, in general or mathematical based pen and paper based calculation, you would be asked this as a settling time. This is similar to settling time only. So when it reaches the steady state, that is where it reaches this settling time. No, so you will be asked to find the TS. So just use the formula for TS. I don't remember that for 2%, for 5%, both formulas will be there. No, 4 by zeta omega and something. I'm not sure about this. Just use the settling time formula. You will get this. That's it. At that time, you will be given the transfer function, so it will be easy for you to find that.
Like this inverse Laplace function that is given, 1
Uh-huh.
minus 2t. So if we put t as 3, then it will give almost 100. Is it like that?
Not like that. For simple system, it is easy to calculate like that. But for second order, if you go for above order system, particularly in second order, you can use this formula.
Okay, so whenever we have to calculate time, we have to use that time
Uh,
settling formula.
yeah, settling time formula. That kind of questions will be asked for second order system only. So you can straight away use those formulas. Okay.
And one more doubt in week 5,
Mm-hmm.
lecture 1,
Week
fifth
5,
slide.
lecture 1, fifth slide. Okay, I think this is fifth slide.
Yes.
Mm.
Ma'am, here it is written that ramp is having slope of 30 Celsius per second. Isn't
Uh-huh.
it 10 degrees Celsius per second in the figure if we see? Isn't it 10?
Let me read the question. Goal is to design a controller to track the reference input temperature signal, which is a RAM input signal. Okay, this is tracking error. This is tracking error plot. They are telling the input temperature signal that is RAM with a slope of 30 degrees Celsius. It's a given information. It is not being represented here. You cannot compare these two. This they are saying for this kind of input, for example, for this ramp input, this is the output and the tracking error, whether it is tracking properly, tracking the input, whether the output is tracking the input properly or not. That kind of analysis you can see using this error. Just they have plotted this EFS, EFS. That's it. For some period of time, for every individual period of time. See,
Okay, so this is
if you zoom on this, just try to find the difference between the red and blue. You will have some minute difference. So it doesn't start at the same stage. And because the scale is in 0 to 50, you cannot see that. So when it comes here around 10 to 20, this becomes larger, right? So that's why this has been peaked, and you can see some deviation is here, and this both gets coincide here. That's why it went down to 10 here, and later it's nearly tracking, so the error also came down. This black is the difference between the red and blue, and the input is this one, this ramp reference, sorry, references. Input is constant, that is 30 degrees Celsius per second. Okay, if you don't have any other questions, we'll wrap up. I'll be here. If you have any doubts, please let me know. Otherwise, we can leave.
Yeah, sure, ma'am. Thank you.
Thank you.
Thank you.